For decades, we crowned the wrong king. Ton 618, the supermassive black hole we called the largest in the universe, the monster that made scientists question if physics had limits, 140 billion times the mass of our sun. An event horizon that could swallow our entire solar system. We built documentaries around it. We wrote papers calculating its impossible scale. We told ourselves this was the edge, the absolute ceiling of how massive a black hole could grow. We were wrong. Phoenix A exists, and it makes Ton 618 look small. Phoenix A is so massive, so incomprehensibly vast, that it breaks the models we used to explain Ton 618 in the first place. The numbers don't just challenge physics, they rewrite what we thought we knew about how black holes form, grow, and die. If this sounds impossible, if you want to see the evidence that turned cosmology upside down, hit that like button and subscribe. This is the story of the black hole that should not exist. Prepare yourselves. We begin. We need to understand what Ton 618 represented before Phoenix A shattered everything. Ton 618 sits roughly 10 billion light-years from Earth, buried in the heart of a quasar so bright it outshines entire galaxies. When astronomers first measured its mass, the number seemed like a mistake. 140 billion solar masses. That is not a black hole. That is a cosmic absurdity. To put this in terms that mean something, imagine our sun as a marble. Ton 618 would be a sphere 50 miles wide. Its event horizon, the point of no return where not even light escapes, stretches 2,700 astronomical units across. That is 67 times the distance from the Sun to Pluto. You could fit our entire solar system inside Ton 618's event horizon, and still have room for 40 more solar systems stacked side by side. For years, Ton 618 held the crown. It defined the upper limit of what we thought black holes could become. Scientists used it as the benchmark, the ultimate endpoint of galactic evolution. Supermassive black holes grow by consuming gas, dust and stars over billions of years, anchored at the centres of galaxies. Ton 618 sat at the theoretical ceiling, the point where radiation pressure from infalling matter should prevent further growth. The Eddington Limit, named after astrophysicist Arthur Eddington, describes this balance. When a black hole feeds, the matter spiralling into it heats up and radiates energy outward. That radiation pushes against new material trying to fall in. At a certain mass, the outward pressure equals the inward gravitational pull. Growth stops. Ton 618 lived right at this edge, massive enough to make physicists uncomfortable, but still explainable within known laws. Then Phoenix A appeared in the data, not through a dramatic discovery or a new telescope pointed at a blank patch of sky. Phoenix A had been hiding in plain sight, catalogued decades ago as just another bright radio source in the constellation Phoenix. Astronomers knew something large sat at the centre of its host galaxy, a supergiant elliptical galaxy billions of light-years away. But the true mass remained uncertain, buried under layers of gas and dust, obscured by the chaos of its accretion disk. When researchers finally compiled enough observations, enough X-ray data, enough radio emissions to calculate the central mass, the number came back wrong. They recalculated, checked the instruments, ran the models again. The number did not change. Phoenix A weighs in at 100 billion solar masses according to the most conservative estimates. Other models push it higher, towards several hundred billion solar masses, dwarfing Ton 618 by factors that make no sense. Therefore, the king we crowned was not the king at all. It was a pretender. Phoenix A had been sitting on the throne the entire time, quietly feeding, growing, violating every limit we thought constrained black hole growth. And here is where the fear begins to creep in. If Ton 618 pushed the boundaries of physics, Phoenix A breaks them. We built our models to explain Ton 618. Those same models cannot explain Phoenix A, which means one of two things. Either our understanding of black hole growth is fundamentally broken, or Phoenix A formed through a process we have never observed, never theorized, and do not yet understand. But mass is only part of the horror. Phoenix A does something Ton 618 does not. It has a jet. A relativistic jet is not a gentle stream of particles. It is a cosmic blowtorch, a beam of matter and energy accelerated to nearly the speed of light, shot out from the poles of a spinning black hole across distances that make galaxies look small. Phoenix A's jet stretches for over 600,000 light-years. To put that in perspective, the Milky Way is roughly 100,000 light-years wide. Phoenix A's jet is 6 times longer than our entire galaxy. If you placed one end at the edge of the Milky Way, the other end would punch through 5 more galaxies stacked end to end. This is not a theoretical construct. We see it. Radio telescopes detect the synchrotron radiation, the electromagnetic scream of electrons spiraling through magnetic fields at relativistic speeds. The Very Large Array in New Mexico, the Australian Square Kilometre Array Pathfinder, and the Low Frequency Array in Europe have all mapped Phoenix A's jet in excruciating detail. It glows in radio wavelengths, a thin line of destruction cutting across the cosmic web like a surgical laser. The energy output is staggering. Phoenix A's jet pumps out more power than 1 trillion suns, not over its lifetime, right now, every second. This energy does not come from nuclear fusion or chemical reactions. It comes from the rotational energy of the black hole itself, a process predicted by Roger Penrose in 1969 and refined by Roger Blandford and Roman Zanarjek in 1977. Here is how it works. A spinning black hole drags space-time around it, a phenomenon called frame dragging. Near the event horizon, space-time itself rotates, forced to follow the black hole's spin. Magnetic fields threading through the accretion disk get twisted, wound up like a spring until they snap outward, channeling plasma and radiation into 2 narrow beams shot out from the poles. The black hole does not create energy from nothing. It converts its own angular momentum, its spin, into the jet. Phoenix A has been doing this for billions of years, bleeding rotational energy into space, and the jet shows no signs of slowing. But the jet is not just bright, it is violent. Anything in its path dies. Stars, planets, gas clouds, entire star-forming regions, all sterilized by a beam of particles moving at 99.9% the speed of light. When the jet slams into the intergalactic medium, the thin gas between galaxies, it creates shock waves that heat the gas to millions of degrees. X-ray telescopes like Chandra and XMM Newton detect these shock fronts, glowing bubbles of superheated plasma carved out by the jet's passage. These bubbles, called radio lobes, are the tombstones of matter that got too close. Phoenix A's radio lobes are enormous. Each lobe is hundreds of thousands of light-years across, inflated by the relentless pressure of the jet. Inside these lobes, conditions are hostile beyond comprehension. Temperatures exceed 10 million degrees. Magnetic fields 1 trillion times stronger than Earth's twist and churn. Cosmic rays, particles accelerated to energies that make the Large Hadron Collider look like a toy, fill the space. If a planet existed inside one of these lobes, its atmosphere would be stripped in seconds. Its surface would be bathed in radiation that would sterilize it down to the bedrock. Life, any form of life we understand, could not survive. And here is the disturbing part. Phoenix A is not unique in having a jet. Many supermassive black holes produce jets, but Phoenix A's jet is different. It is too powerful. The energy required to sustain a jet of this size and luminosity for billions of years exceeds what standard accretion models predict. A black hole feeding at the Eddington Limit, the maximum rate at which it can consume matter without blowing itself apart with radiation pressure, should not produce a jet this energetic. Therefore, Phoenix A is either feeding faster than it should, spinning faster than it should, or both. Every explanation leads to the same conclusion. Phoenix A is operating outside the rules. The jet also tells us something terrifying about Phoenix A's history. Jets require spin. A non-rotating black hole, a Schwarzschild black hole, cannot produce a jet. The more spin, the more powerful the jet. Phoenix A's jet suggests it is a maximally rotating black hole, a Kerr black hole spinning at or near the theoretical limit. How does a black hole reach maximum spin? By consuming matter in an organized way, with all the infalling material rotating in the same direction, adding angular momentum with every meal. This means Phoenix A did not grow chaotically. It fed deliberately, systematically over billions of years, building spin and mass in lockstep. This is not a black hole that formed from random mergers and collisions. This is a black hole that optimized itself, but optimization requires fuel. Phoenix A sits at the center of a massive elliptical galaxy, a galaxy that should have exhausted its gas reserves billions of years ago. Elliptical galaxies are old, red, quiet. They do not form new stars. They do not have vast reservoirs of cold gas waiting to be consumed. Yet Phoenix A is feeding. The accretion disk glows in X-rays, proof that matter is still spiraling inward. Where is this matter coming from? The galaxy should be empty. The jet should have cleared out any remaining gas, yet Phoenix A continues to eat. And this brings us to the question no one wants to ask. How big can Phoenix A get before something stops it? Let's talk about the number that should not exist. Phoenix A's mass, depending on the model and the dataset, ranges from 100 billion to possibly 300 billion solar masses. The uncertainty itself is terrifying. We cannot pin down Phoenix A's exact mass because it is so large that our measurement techniques start to break. But let us take the conservative estimate. 100 billion solar masses. If the Sun were a grain of sand 1 millimeter across, Phoenix A would be a sphere 150 kilometers wide, not a mountain range. If you stood at one edge, the horizon would curve away before you could see the other side. Ton 618, the previous record holder, weighs 140 billion solar masses. On paper, Phoenix A and Ton 618 seem close. But black hole mass does not scale linearly with size. The event horizon radius grows proportionally with mass. Ton 618's event horizon is roughly 2,700 astronomical units across. Phoenix A, even at the lower estimate, has an event horizon approaching 3,000 astronomical units. That extra few hundred astronomical units represents billions of cubic astronomical units of additional volume. Space where light cannot escape. Space where time stops. But the real horror is not the size. It is what the size implies. Black holes grow by consuming mass. Every star, every planet, every atom of gas that crosses the event horizon adds to the black hole's mass. To reach 100 billion solar masses, Phoenix A had to consume the equivalent of 100 billion stars. Our galaxy contains roughly 400 billion stars. Phoenix A has eaten a quarter of the Milky Way's worth of matter, and it did this while sitting at the center of a single galaxy. A galaxy that contains perhaps 1 trillion stars, but most of that mass is locked in stars too far away to fall in. The feeding rate required to build Phoenix A defies standard models. Supermassive black holes grow slowly. A typical supermassive black hole at the center of a galaxy might consume a few solar masses per year. At that rate, building a 100 billion solar mass black hole takes tens of billions of years. But the universe is only 13.8 billion years old. Phoenix A's host galaxy formed perhaps 12 billion years ago. That gives Phoenix A 12 billion years to grow from a seed black hole, probably a few hundred or thousand solar masses, to its current incomprehensible size. The math does not work. To grow that large in that time, Phoenix A must have been feeding at rates far exceeding the Eddington Limit for most of its existence. The Eddington Limit is not a suggestion. It is a physical barrier. When matter falls into a black hole, it heats up. The accretion disk around a feeding black hole glows brighter than entire galaxies because in falling matter converts gravitational potential energy into heat and light. This radiation pushes outward. At a certain luminosity, the radiation pressure equals the gravitational pull. New matter cannot fall in. Growth stops. For a black hole the size of Phoenix A, the Eddington Limit caps the feeding rate at roughly 2 solar masses per year. At that rate, growing to 100 billion solar masses takes 50 billion years. Phoenix A does not have 50 billion years. It has 12 billion, maybe less. Therefore, Phoenix A cheated. It found a way around the Eddington Limit. One possibility is super Eddington accretion. If matter falls in faster than radiation can push it away, the black hole can grow faster than the limit allows. But super Eddington accretion is unstable. The excess radiation should blow apart the accretion disk, shutting down feeding entirely. Observations of super Eddington black holes show chaotic, flickering luminosity. Phoenix A's emission is steady, sustained, relentless. It is not flickering. It is not unstable. It is feeding at a rate that should not be possible and doing it calmly. Another possibility is that Phoenix A grew through mergers. When two black holes collide, they combine their masses instantly, bypassing the slow process of accretion. If Phoenix A formed from dozens or hundreds of smaller black hole mergers, it could reach its current size faster. But mergers leave signatures. Gravitational waves ripple out from colliding black holes, carrying away energy and angular momentum. The LIGO and Virgo detectors have recorded dozens of black hole mergers, and every merger follows predictable patterns. Phoenix A shows no evidence of recent major mergers. Its spin, inferred from the jet's power, suggests a smooth, organised growth history, not the chaotic spin axis changes that mergers cause. A third possibility is more disturbing. Phoenix A may have started big. Primordial black holes formed in the first moments after the Big Bang, could have seeded the universe with black holes far larger than any star could produce. If Phoenix A began as a primordial black hole weighing millions or billions of solar masses, it would have a head start bypassing the slow early growth phase. But primordial black holes are theoretical. We have never confirmed one exists. Using them to explain Phoenix A feels like invoking magic. So we are left with a black hole that is too massive, too fast-growing, and too stable to fit our models, and it gets worse. Phoenix A is not alone. Astronomers have found other black holes approaching or exceeding 100 billion solar masses. Holmberg 15A, another supergiant elliptical galaxy, hosts a black hole estimated at 170 billion solar masses. IC 1101, a galaxy in the Virgo cluster, may contain a black hole of similar size. These discoveries suggest Phoenix A is not a fluke. It is part of a population. There are black holes out there, plural, that break the rules. We just did not know where to look. The existence of multiple ultra-massive black holes means our models are not slightly wrong. They are fundamentally broken. Either black holes can grow faster than we thought, through mechanisms we do not understand, or the universe is older than we think, giving black holes more time to grow. Neither option is comforting. Both require rewriting decades of established astrophysics, and both leave us with the same haunting question. If black holes can grow this large, is there a limit at all? Or can they just keep feeding, keep growing, until they consume everything? Phoenix A is not finished. It is still feeding. The accretion disk still glows, the jet still fires. Right now, at this moment, Phoenix A is adding mass, growing heavier, expanding its event horizon. And we have no idea when it will stop. The jet is not a side effect, it is a weapon. Phoenix A's relativistic jet carries energy equivalent to the total power output of 10 trillion stars, not over billions of years, every second. This energy tears through space at 99.97% the speed of light, a lance of plasma and magnetic fields that has been firing continuously for at least 100 million years, possibly longer. The jet does not fade with distance, it does not dissipate. It punches through the intergalactic medium, carving tunnels in space that glow in radio wavelengths like scars across the cosmos. To understand what this jet does, you need to understand what it hits. The intergalactic medium is not empty. It is filled with thin gas, mostly hydrogen and helium, left over from the Big Bang. The density is absurdly low, about 1 atom per cubic meter, a trillion times less dense than the air you're breathing. But across millions of light years, even thin gas adds up. When Phoenix A's jet slams into this gas at near light speed, it does not gently push it aside. It shocks it, heats it, ionizes it. The gas temperature jumps from a few thousand degrees to 10 million degrees in an instant. Electrons are ripped from atoms. The gas glows in X-rays, visible to telescopes like Chandra and XMM Newton, as bubbles of superheated plasma expanding outward from the jet's path. These bubbles, the radio lobes, are not static. They grow. Every year, Phoenix A's jet pumps more energy into them, inflating them like cosmic balloons. The northern lobe stretches 300,000 light-years from the black hole. The southern lobe mirrors it, extending another 300,000 light-years in the opposite direction. Together, they span 600,000 light-years, a distance so vast that light takes 600,000 years to cross from one end to the other. Inside these lobes, the environment is hostile beyond anything we experience in our local universe. Thread through the plasma. Cosmic rays, particles accelerated to energies exceeding 10 to the 20th electron volts, fill the space. For comparison, the most powerful particle accelerator humanity has ever built, the Large Hadron Collider, accelerates protons to 10 to the 13th electron volts. The particles in Phoenix A's jet are 10 million times more energetic. What happens to a galaxy caught in this jet? We do not have to guess. We have seen it. Observations of other galaxies with powerful jets show the damage. Star formation stops. The cold gas needed to form new stars is heated and expelled. Molecular clouds, the nurseries where stars are born, are torn apart by the jet's passage. Entire regions of galaxies become sterile, unable to produce new stars for billions of years. Phoenix A's jet is more powerful than almost any other jet we've observed. The sterilization radius, the distance from the jet where star formation becomes impossible, likely extends tens of thousands of light years on either side. Any galaxy unlucky enough to intersect Phoenix A's jet would see its star-forming regions shut down within millions of years. But the destruction is not limited to galaxies in the jet's direct path. The radio lobes themselves affect a much larger volume. As the lobes expand, they push against the intergalactic medium, creating pressure waves that propagate outward. These waves heat the gas in neighbouring galaxies, disrupting star formation even in systems far from the jet itself. Phoenix A is not just killing its immediate surroundings, it is poisoning the cosmic neighbourhood, creating a dead zone hundreds of millions of light years across where galaxies struggle to form new stars. The energy source for this jet is Phoenix A's spin. The black hole rotates, dragging spacetime with it. Magnetic fields anchored in the accretion disk get twisted by this rotation, wound tighter and tighter until they snap outward, channeling energy into the jet. This process, the Blanford-Zanayak mechanism, is brutally efficient. It can extract up to 29% of a black hole's rest mass energy as jet power. For Phoenix A, with its 100 billion solar masses, this means the jet could theoretically tap into an energy reservoir equivalent to 29 billion suns converted entirely to energy. That is more energy than our galaxy will produce over its entire remaining lifetime. But there is a cost. Every earg of energy the jet carries away comes from Phoenix A's rotational energy. The black hole is slowing down. Spin is being bled into space, converted into the jet's kinetic energy and magnetic fields. Over billions of years, Phoenix A's rotation rate should decrease. The jet should weaken. Eventually it should shut off entirely as the black hole's spin drops below the threshold needed to power the Blanford-Zanayak process. Yet Phoenix A's jet shows no signs of weakening. Radio observations spanning decades show consistent luminosity. The jet is not fading. This means Phoenix A is replenishing its spin as fast as it loses it. Every bit of matter that falls into the black hole adds angular momentum, keeping the spin high, keeping the jet alive. This creates a feedback loop. The jet clears out gas from the surrounding environment, which should starve the black hole and shut down the jet. But somehow, Phoenix A continues to feed, continues to spin, continues to fire. The jet sustains itself through a process we do not fully understand. Either Phoenix A has access to a fuel source we cannot see, or the jet itself creates conditions that funnel more matter toward the black hole. Some models suggest the jet's magnetic fields can redirect gas from the outer regions of the galaxy back toward the center, creating a self-feeding cycle. If true, Phoenix A is not just a black hole with a jet, it is a machine, optimized over billions of years to maximize both feeding and energy extraction. The jet also tells us something about Phoenix A's future. Black holes do not live forever. Hawking radiation, a quantum mechanical process, causes black holes to slowly evaporate, losing mass over incomprehensibly long timescales. For a black hole as massive as Phoenix A, the evaporation time exceeds 10 to the 100 years, far longer than the current age of the universe. But the jet accelerates the process. By converting spin to energy, the jet drains Phoenix A faster than Hawking radiation ever could. In trillions of years, long after the last star is burned out, Phoenix A will still be here, spinning down, its jet gradually weakening as the black hole loses angular momentum. Eventually the jet will sputter and die. Phoenix A will become a non-rotating black hole, a cold, dark sphere of warped space-time, unable to produce jets, unable to feed efficiently, locked in a slow death spiral that will take longer than the universe has time for. But that is the far future. Right now, Phoenix A is alive, the jet is firing, and the destruction continues. Phoenix A is eating, right now. The evidence is undeniable. X-ray observations show a glowing accretion disk, a swirling maelstrom of superheated gas spiraling into the event horizon. The disk radiates across the electromagnetic spectrum, from radio waves to gamma rays, a signature that only appears when a black hole is actively feeding. The luminosity tells us how fast matter is falling in. Phoenix A is consuming roughly 10 to 20 solar masses per year. That is 10 to 20 times the mass of our Sun, converted from orbiting gas clouds into doomed particles crossing the event horizon every single year. To put this in perspective, imagine the Sun disappearing. Gone. Then imagine 19 more suns vanishing. That is 1 year of Phoenix A's diet. This has been happening for billions of years. The total mass consumed is staggering, but what makes it terrifying is that Phoenix A should have run out of food long ago. The black hole sits at the center of a supergiant elliptical galaxy, a galaxy type defined by its lack of star formation, its absence of cold gas, its evolutionary dead end. Elliptical galaxies are old. They formed their stars billions of years ago in violent bursts, exhausting their gas reserves in the process. What remains are ancient red stars slowly dying, with almost no new material to feed a central black hole. Yet Phoenix A feeds. The accretion disk glows with the heat of infalling matter. Spectroscopic observations reveal ionized gas moving at thousands of kilometers per second. Gas that is being funneled toward the black hole from somewhere. Where is it coming from? The galaxy itself cannot supply this much material. Stellar winds from dying stars contribute some mass, but nowhere near enough to sustain Phoenix A's appetite. The math does not work. A typical elliptical galaxy loses maybe 1 solar mass per year to stellar winds. Phoenix A needs 10 to 20 times that. There has to be another source. One possibility is that Phoenix A is cannibalizing its host galaxy from the inside out. Stars that wander too close to the black hole are torn apart by tidal forces long before they reach the event horizon. This process, called tidal disruption, shreds a star into a stream of gas that spirals into the black hole over months or years. Tidal disruption events are rare. We observe a few per year across the entire observable universe. But Phoenix A, with its immense gravitational reach, could be disrupting stars at a higher rate. If Phoenix A tears apart one star every few years, that adds up. Over millions of years, thousands of stars get shredded feeding the black hole. But even this is not enough. The numbers still fall short. Another possibility is that Phoenix A is fed by galactic cannibalism. Supergiant elliptical galaxies like Phoenix A's host often sit at the centers of galaxy clusters, massive gravitational wells where smaller galaxies fall in and get torn apart. When a smaller galaxy collides with a central giant, its stars are scattered, but its gas is funneled toward the center. This gas, compressed and heated by the collision, flows into the supermassive black hole, providing a fresh meal. Observations of Phoenix A's host galaxy show faint tidal streams, ghostly arcs of stars that hint at past galactic mergers. Phoenix A may be feeding on the remnants of galaxies that fell into its host billions of years ago, gas clouds that are only now reaching the black hole after eons of slow inward drift. But there is a darker explanation: dark matter. We know dark matter exists because we see its gravitational effects. Galaxies rotate too fast. Galaxy clusters hold together too tightly. The cosmic web, the large-scale structure of the universe, requires 5 times more mass than we can see. This invisible mass, dark matter, does not interact with light. It does not emit, absorb, or reflect radiation. It only pulls, gravitationally, and it is everywhere. Simulations of galaxy formation show that dark matter forms vast halos around galaxies, halos that extend far beyond the visible stars. Phoenix A sits at the center of one of the most massive dark matter halos in the universe. Dark matter does not fall into black holes easily. It moves too fast, orbiting in the halo rather than spiraling inward. But over billions of years, interactions with ordinary matter, gravitational encounters, and dynamical friction can cause dark matter particles to lose energy and sink toward the center. If even a tiny fraction of Phoenix A's dark matter halo has fallen into the black hole, it could account for the missing mass. Dark matter does not glow. It does not leave X-ray signatures. It simply adds to the black hole's mass, silently, invisibly, over cosmic timescales. Phoenix A may have grown so large not by consuming visible matter, but by eating the invisible scaffolding of its galaxy. This idea is terrifying because it means Phoenix A's growth is not limited by the amount of gas and stars in its galaxy. It is limited by the dark matter halo, a reservoir of mass far larger than all the visible matter combined. If Phoenix A can tap into this reservoir, it could grow indefinitely, far beyond any limits we currently understand. The Eddington Limit, the theoretical cap on black hole growth, only applies to matter that radiates. Dark matter does not radiate. It does not create radiation pressure. A black hole feeding on dark matter faces no Eddington Limit. It can grow as fast as dark matter falls in. We do not know if this is happening. We cannot detect dark matter directly, but the circumstantial evidence is compelling. Phoenix A is too massive. It is feeding too fast. It sits in a galaxy that should be empty, and it resides at the center of one of the universe's most massive dark matter halos. The pieces fit. Phoenix A may be the first black hole we have found that is actively consuming dark matter in significant quantities, a process that could explain not just its size, but the existence of other ultramassive black holes like it. The accretion disk itself is a nightmare of physics. Gas spiraling into Phoenix A reaches temperatures exceeding 10 million degrees. At these temperatures, atoms are ionized, electrons ripped free, leaving a plasma of charged particles. This plasma radiates X-rays, the signature we detect with space telescopes. But the disk is not uniform. It is turbulent, chaotic, threaded with magnetic fields that create instabilities. Magnetorotational instability, a process where magnetic fields amplify turbulence in the disk, causes clumps of matter to spiral inward faster than smooth accretion would allow. This turbulence may be how Phoenix A feeds faster than the Eddington Limit permits. The disk is not a smooth flow. It is a storm, with matter falling in through narrow channels, bypassing the radiation pressure that should slow it down. And the disk is massive. The amount of matter currently in Phoenix A's accretion disk, orbiting just outside the event horizon, is equivalent to thousands of solar masses. This is not a thin film of gas. It is a dense, swirling disk with its own gravity, its own dynamics, its own internal structure. Parts of the disk may be forming temporary structures, perhaps even short-lived stars or planetary mass objects that quickly spiral inward and get consumed. The disk is a feeding ground, a slaughterhouse where matter is processed, heated, and destroyed before crossing the event horizon. Phoenix A has been feeding for billions of years. It will feed for billions more, and every meal makes it stronger. The Eddington Limit is supposed to be unbreakable. It is not a theory. It is a consequence of basic physics, derived from the balance between gravity pulling matter inward and radiation pushing it outward. When Arthur Eddington calculated this limit in the early 20th century, he gave us a fundamental constraint on how fast any object can grow by accretion. For a black hole, the equation is simple. The maximum luminosity equals 4 pi times the gravitational constant times the black hole's mass times the speed of light, divided by the Thomson scattering cross-section. This sounds abstract, but the result is concrete. A black hole can only feed as fast as its radiation allows. The Eddington Limit sets the maximum accretion. Any faster, and the radiation from the accretion disk becomes so intense it blows away incoming matter before it can fall in. This is not speculation. We observe Eddington limited accretion in countless black holes across the universe. Quasars, the brightest objects in the cosmos, shine at or near their Eddington luminosity. When they exceed it, even briefly, we see outflows, winds of gas being expelled at thousands of kilometers per second. The system self-regulates. Feed too fast, blow away your food, slow down, repeat. Phoenix A does not follow this script. Observations suggest it is accreting at 10 to 20 solar masses per year, 5 to 10 times the Eddington rate. This sounds like we made a mistake. We check the luminosity measurements. We recalibrate the distance estimates. We run the models with different assumptions about the accretion disk's temperature, opacity, and geometry. The conclusion does not change. Phoenix A is feeding faster than it should be able to, and it has been doing this for long enough to grow to 100 billion solar masses in less than the universe's lifetime. This should be impossible, but the black hole exists. Therefore, our understanding is incomplete. Several mechanisms could allow super Eddington accretion, but none of them work cleanly for Phoenix A. The first is geometrical beaming. If the accretion disk is thick and the radiation escapes primarily along the rotational axis, perpendicular to the disk, then an observer looking at the disk edge-on would see lower luminosity than the true output. The black hole could be feeding at super Eddington rates, but the radiation is beamed away from us, making it look dimmer. This works for some systems, but Phoenix A's orientation, inferred from the jet's angle and the disk's spectral properties, does not support strong beaming. We are not looking at it edge-on. The luminosity we measure is close to the true luminosity. The second possibility is that the accretion flow is not a thin disk, but a thick radiation pressure-supported torus. In this geometry, radiation gets trapped inside the inflowing matter, unable to escape and push back effectively. The matter falls in faster because the radiation cannot get out in time to stop it. This is called advection-dominated accretion. The radiation is advected, carried inward with the flow, rather than radiated outward. Some of the energy released by infalling matter crosses the event horizon before it can be converted to outward pressure. This allows accretion rates above the Eddington limit. But advection-dominated flows are inefficient. They produce lower luminosity per unit mass accreted. Phoenix A is luminous. Its X-ray and radio emission are consistent with efficient accretion, not advection-dominated flow. A third mechanism is photon trapping. In extreme cases, when matter falls in so fast that the density becomes enormous, photons cannot escape the flow. They scatter off electrons and ions so many times that they lose their outward momentum and get dragged inward with the infalling matter. The radiation is trapped, unable to create the pressure needed to halt accretion. This allows super Eddington rates, but it requires accretion rates hundreds or thousands of times the Eddington limit. Phoenix A is super Eddington, but not by that much. Photon trapping does not fit. We are left with an uncomfortable possibility. Phoenix A's growth history may not have been continuous. Perhaps it did not feed at super Eddington rates for billions of years. Perhaps it grew in bursts, short periods of extremely rapid accretion interspersed with long, dormant phases. During the bursts, it could exceed the Eddington limit dramatically for millions of years at a time, consuming vast amounts of matter before the radiation pressure built up enough to shut down feeding. Then it would go quiet, dormant for hundreds of millions of years, until another galactic merger or gas inflow event triggered a new feeding frenzy. Averaged over billions of years, the growth rate looks moderate. But in reality, Phoenix A grew in violent, chaotic episodes that our models do not capture. There is observational support for this. Studies of quasar populations show that supermassive black holes do not grow smoothly. They have active phases, when they shine as quasars, and quiescent phases, when they fade into darkness. The duty cycle, the fraction of time a black hole spends in the active phase, is only about 10%. Phoenix A may have spent 90% of its life dormant, invisible, accumulating gas in its outer regions. Then, every few hundred million years, something triggers inflow. A galactic merger, a gravitational instability in the surrounding gas, a passing galaxy that stirs up the intergalactic medium. The gas falls in rapidly, Phoenix A lights up, feeds at super Eddington rates for a few million years, and then shuts down again. Repeat this cycle dozens of times over 12 billion years, and you can build without violating the Eddington limit continuously. But this creates another problem. If Phoenix A grows in bursts, we should see evidence of past outbursts. The radio lobes, the cavities carved by the jet, should show multiple generations of activity, like tree rings recording each feeding episode. Some radio galaxies do show this. They have inner lobes from recent activity and faint outer lobes from ancient outbursts. Phoenix A's radio lobes are enormous, but they appear to be from a single ongoing episode. There are no clear signs of multiple generations. Either Phoenix A's current active phase has lasted so long it erased evidence of past cycles, or Phoenix A's growth history is different from other black holes. Another disturbing possibility is that the Eddington limit does not apply the way we think it does for black holes this massive. The limit assumes spherical symmetry, matter falling in from all directions. But real accretion is not spherical. It happens through a disk. The disk is thin in the vertical direction but extended radially. Radiation escapes primarily perpendicular to the disk, along the rotational axis. Matter falls in through the disk's equatorial plane. If the radiation and the infalling matter are geometrically separated, the radiation might not effectively block inflow. The Eddington limit becomes less of a hard barrier and more of a guideline. For ultramassive black holes with highly structured accretion disks, the effective limit could be higher than the simple spherical calculation suggests. This is unsatisfying. It feels like we're inventing excuses to explain why our models fail. But science advances by confronting failures. Phoenix A exists. It is too massive. It grew too fast. Either our models are wrong, or the universe found a loophole we have not discovered yet. Both options force us to rethink fundamental assumptions about black hole growth. And both options suggest that Phoenix A is not the largest black hole possible. If the Eddington limit can be exceeded, if growth can happen faster than we calculated, then there may be even larger black holes out there. waiting to be found. Black holes that make Phoenix A look small, and we would have no framework to explain them. Every explanation we construct for Phoenix A collapses under scrutiny. Start with the most straightforward theory. Phoenix A formed early and grew steadily. Supermassive black holes are thought to originate from seed black holes in the early universe, either stellar mass black holes from the first generation of stars or intermediate mass black holes from direct collapse of gas clouds. These seeds, weighing anywhere from tens to hundreds of thousands of solar masses, then grow by accreting gas over billions of years. For Phoenix A to reach 100 billion solar masses from a 100 solar mass seed requires growing by a factor of 1 billion. At the Eddington Limited rate, this takes roughly 40 billion years. The universe is 13.8 billion years old. The math fails immediately. Increase the seed mass. Suppose Phoenix A started as a 100,000 solar mass black hole, formed by direct collapse of a massive gas cloud in the early universe. Now it only needs to grow by a factor of 1 million. That still requires over 30 billion years of Eddington Limited accretion. Still impossible. Push the seed mass higher. 1 million solar masses, 10 million. Even with a 10 million solar mass seed, an object we have never observed and have no confirmed mechanism to produce, Phoenix A needs over 20 billion years to grow. Every path leads to the same dead end. Phoenix A cannot have grown through steady accretion, no matter how massive the seed. So we pivot to mergers. Black holes collide. When galaxies merge, their central black holes eventually spiral together and coalesce, combining their masses in a fraction of a second. This bypasses accretion entirely. Phoenix A could be the product of hundreds or thousands of black hole mergers over cosmic time. Take 100 black holes, each weighing 1 billion solar masses, smash them together, and you get Phoenix A. Simple. But this theory disintegrates when we examine the details. First, where do the 1 billion solar mass black holes come from? Each of those requires its own growth history, its own impossibly fast accretion, or its own chain of mergers. We have just pushed the problem down one level without solving it. Second, black hole mergers are not instantaneous on cosmic scales. When two galaxies collide, their central black holes are initially separated by thousands of light years. They have to sink toward the center through a process called dynamical friction, where gravitational interactions with stars slow them down. This takes hundreds of millions of years. Then, when the black holes get within a few light years of each other, they form a binary, orbiting each other. The binary shrinks through gravitational wave emission, but this final stage can take millions more years. For Phoenix A to result from hundreds of mergers, we need hundreds of galaxy collisions, each delivering a black hole that takes hundreds of millions of years to merge. The timeline barely fits within the age of the universe, and that assumes continuous mergers with no gaps. Third, mergers leave signatures. When black holes collide, they emit gravitational waves, ripples in space-time that carry observatories have detected dozens of black hole mergers, and every event shows characteristic patterns. A chirp signal as the black holes spiral together, a ring down as the merged black hole settles into a stable state. These signals tell us about the masses and spins of the merging black holes. If Phoenix A formed from many mergers, its spin should be chaotic, the result of black holes colliding from random directions with random spin orientations. But Phoenix A's jet suggests high, organized spin. The black hole is rotating rapidly in a single direction, not tumbling chaotically. This points to smooth accretion, not violent mergers. Fourth, there is the final parsec problem. When two black holes in a binary get within about 1 parsec, roughly 3 light years, of each other, dynamical friction becomes inefficient. There are not enough stars in the core to carry away the binary's energy. The black holes stall, orbiting each other indefinitely without merging. Theorists have proposed solutions: interactions with a circumbinary gas disk, 3-body encounters with a third black hole, or gravitational wave emission becoming strong enough to close the gap. But none of these mechanisms are guaranteed to work. Many black hole binaries may be stuck, unable to merge, scattered throughout the universe as permanent pairs. If the final parsec problem is real, then building Phoenix A through mergers becomes even harder. Many of the mergers we are counting on may never have completed. We try another angle: primordial black holes. In the first fraction of a second after the Big Bang, quantum fluctuations in the density of the universe could have created regions dense enough to collapse directly into black holes. These primordial black holes would not form from stars. They would be born massive, potentially ranging from tiny subatomic masses to millions of solar masses. If Phoenix A started as a primordial black hole weighing 10 million or even 1 billion solar masses, it gets a massive head start. The growth problem becomes easier, but primordial black holes are purely theoretical. We have no confirmed detections. Observations of the cosmic microwave background, gravitational lensing surveys, and gamma-ray bursts all place strict limits on how many primordial black holes can exist and how massive they can be. The constraints rule out large populations of massive primordial black holes. They might exist in small numbers, but invoking them to explain every ultramassive black hole feels like giving up. We are saying the universe handed Phoenix A a billion solar mass gift at birth, and we have no evidence this ever happens. Then there is the dark matter hypothesis, the idea we touched on earlier. If dark matter particles can lose energy and fall into black holes, Phoenix A could have been feeding on an invisible reservoir far larger than any gas cloud. Dark matter makes up 85% of the universe's matter. Even a small fraction of a galaxy's dark matter halo falling into the central black hole could provide enormous mass. But this theory has problems too. Dark matter particles, whatever they are, interact only through gravity. They do not collide with each other or with ordinary matter except gravitationally. This makes them very hard to capture. They orbit in the dark matter halo at high speeds, typically hundreds of kilometers per second. For them to fall into the black hole, they need to lose energy. Without collisions, without friction, how do they slow down? Some models propose that dark matter can annihilate, particle and antiparticle meeting and releasing energy. If this happens near the black hole, the energy release could affect nearby dark matter particles, causing them to lose speed and fall in. But dark matter annihilation rates are highly uncertain. We do not even know what dark matter is. Calling on it to explain Phoenix A is building one unknown on top of another. Every model we construct, every mechanism we propose, either requires conditions we have never observed, timescales longer than the universe allows, or processes we do not understand. Phoenix A should not exist, yet it does. The observations are clear, the mass estimates are robust, we are not misinterpreting the data. Phoenix A is real. Therefore our theories are incomplete. Something is missing. Some process, some pathway to rapid black hole growth exists in nature but eludes our models. Phoenix A is not an anomaly to be explained away, it is a clue, a signpost pointing toward physics we have not yet discovered, and that is what makes it terrifying. We're confronted with an object that breaks our understanding, and we have no idea what we're missing. Dark matter is the skeleton of the universe. Galaxies, galaxy clusters, the entire cosmic web, all of it hangs on a scaffolding we cannot see. Roughly 85% of the matter in the universe does not emit light, does not absorb light, does not interact with electromagnetic radiation at all. We know it exists only for the visible stars and gas to hold them together. Galaxy clusters contain more gravitational mass than all their galaxies combined. Gravitational lensing, the bending of light around massive objects, reveals vast halos of invisible matter surrounding every galaxy. Dark matter is everywhere, outnumbering ordinary matter 5-1, and ever observed. Simulations of galaxy formation show how dark matter shapes the universe. In the early universe, dark matter clumped together first, forming gravitational wells that pulled in ordinary matter. Gas fell into these wells, condensed, formed stars, built galaxies. The dark matter halo remains, an invisible sphere extending far beyond the visible galaxy. For a supergiant elliptical galaxy like Phoenix A's host, the dark matter halo likely extends several million light-years, containing trillions of solar masses. Most of this mass orbits in the halo's outer regions, moving too fast to fall into the center. But over billions of years, gravitational interactions, dynamical friction, and random encounters cause some inward. A tiny fraction of the halo, perhaps 1% or less, could have migrated to the galaxy's core over cosmic time. That 1%, from a halo containing trillions of solar masses, amounts to tens of billions of solar masses, enough to build Phoenix A. This is not wild speculation. Dark matter must accumulate at galaxy centers. Simulations consistently show density spikes in the central regions, where dark matter particles on low-energy orbits pile up. The question is whether this dark matter can actually fall into the black hole. Dark matter particles, whatever they are, do not collide with ordinary matter in the way atoms do. They pass through normal matter almost unimpeded, interacting only gravitationally. This makes them difficult to capture. A dark matter particle on a fast orbit will swing past the black hole and fly back out into the halo. For it to be captured, it needs to lose energy. Without collisions, without friction, this is hard. But not impossible. One mechanism is gravitational scattering. Dark matter particles interact gravitationally with stars, gas clouds, and each other. Over billions of years, countless gravitational encounters gradually randomize the particles' orbits. Some gain energy and get kicked to higher orbits. Others lose energy and sink deeper into the gravitational well. This process, called violent relaxation when it happens quickly during galaxy formation, or two-body relaxation when it happens slowly over time, causes a small but steady flow of dark matter toward the center. The black hole, sitting at the absolute bottom of the potential well, captures any dark matter that loses enough energy to cross the event horizon. Another possibility involves dark matter self-interaction. Most dark matter models assume the particles are collisionless, interacting only through gravity. But some theories propose that dark matter particles can scatter off each other through a new unknown force. If dark matter has even weak self-interactions, particles in the dense central regions of galaxies could collide, lose energy, and sink toward the black hole faster than gravity alone allows. Observations of galaxy cluster collisions like the Bullet cluster place limits on how strong these self-interactions can be. But within those limits, there is room for dark matter to behave in ways that enhance capture by black holes. A third mechanism is dark matter annihilation. If dark matter is made of particles and antiparticles, as many theories suggest, then collisions between them would release energy. Near a supermassive black hole, where dark matter density is highest, annihilation rates increase. The energy released, possibly in the form of gamma rays or other particles, could affect nearby dark matter, heating it or altering its distribution. This feedback might actually slow dark matter capture, or it might create conditions that funnel more dark matter inward. The details depend on the unknown properties of dark matter, making this mechanism speculative but not impossible. Observational evidence hints that dark matter and black holes are connected. Studies of dwarf galaxies, small galaxies dominated by dark matter, show correlations between dark matter halo properties and central black hole masses. Galaxies with denser dark matter halos tend to have more massive central black holes, even when controlling for stellar mass and other factors. This suggests that dark matter plays a role in black hole growth, either by providing fuel directly or by shaping the gas flows that feed the black hole. Phoenix A, in one of the universe's most extreme dark matter environments, could be the ultimate expression of this connection. But dark matter feeding comes with a profound implication. If Phoenix A grew primarily by consuming dark matter, rather than stars and gas, then most of its mass is invisible matter that never radiated, never produced light, never left an observational signature beyond its gravitational pull. The black hole could have been growing silently for billions of years, swelling to enormous size without ever becoming a bright quasar or active galactic nucleus. Only recently, in the last few 100 million years, has Phoenix A started consuming significant amounts of ordinary matter, lighting up the accretion disk and jet that we now observe. The black hole we see today is not Phoenix A in its growth phase. It is Phoenix A after it has already grown, now feeding on the leftover scraps of visible matter in a galaxy it has already hollowed out. This paints a disturbing picture. Across the universe, there may be thousands or millions of ultramassive black holes that grew through dark matter accretion. Black holes that never shone brightly, never announced their presence, and remain hidden in the centers of galaxies we think are quiet. We find the ones like Phoenix A only when they happen to consume enough ordinary matter to produce observable emissions. The rest are invisible, lurking, waiting. The census of supermassive black holes, the population statistics we have built from decades of observations, might be catastrophically incomplete. We may have missed the majority of the universe's most massive black holes because they fed on matter we cannot see. Dark matter also provides a solution to the Eddington Limit problem. The Eddington Limit applies to radiating matter, when gas produces radiation, and that radiation creates outward pressure, but heat up. It does not create consumed dark matter as fast as the particles fall in, limited only by the supply rate and orbital dynamics. If Phoenix A spent most of its life feeding on dark matter, It could grow at super Eddington rates without violating any physical laws. The growth barrier disappears. Of course, this hypothesis is maddeningly difficult to test. Dark matter is invisible. We cannot directly observe it falling into Phoenix A. We cannot measure the dark matter accretion rate. All we can do is look for indirect evidence: anomalously rapid black hole growth, correlations between black hole mass and dark matter halo properties, and possible signatures from dark matter annihilation near the event horizon. Gamma-ray telescopes like Fermi and upcoming observatories like the Cherenkov Telescope Array search for excess gamma rays from galaxy centers that could indicate dark matter annihilation. So far, the results are inconclusive. We see gamma rays, but they can be explained by ordinary astrophysical processes without invoking dark matter. Phoenix A forces us to confront how little we understand about the universe's dominant form of matter. Dark matter shapes galaxies, drives cosmic structure, and may feed the largest black holes. Yet we do not know what it is made of. Decades of experiments searching for dark matter particles, from deep underground detectors to particle colliders, have found nothing conclusive. Dark matter remains the universe's greatest mystery, and Phoenix A, the black hole that should not exist, may be our best clue that dark matter does more than just pull. It feeds, it falls, it builds monsters in the dark. The jet's power output defies comprehension. 10 trillion times the luminosity of the sun, sustained for over 100 million years, possibly longer. This is not a brief flare or a temporary outburst. This is continuous, relentless energy extraction on a scale that dwarfs anything else in the nearby universe. To understand where this energy comes from, we need to look at the black hole itself, not as a static object, but as a spinning dynamo that converts its own rotation into electromagnetic fury. Black holes can spin, carries angular momentum. The black hole absorbs this angular momentum, building up rotational energy. A non-rotating black hole, called a Schwarzschild black hole, is perfectly spherical. Its event horizon is a simple sphere with a radius determined only by mass. But a spinning black hole, a Kerr black hole, is different. Rotation drags space-time around the black hole, creating a region called the ergosphere where space-time itself is forced to rotate. Anything in the ergosphere, even light, cannot remain stationary. It is dragged along by the black hole's spin. The ergosphere is the key. In 1969, physicist Roger Penrose realized that you could extract energy from a rotating black hole by dropping an object into the ergosphere, splitting it into two pieces, and allowing one piece to fall into the event horizon while the other escapes. If done correctly, the escaping piece carries away more energy than the original object had. This energy comes from the black hole's rotational energy. The black hole slows down slightly, and the escaping particle gains energy. This is the Penrose process. It is not science fiction. It is a consequence of general relativity, confirmed by decades of mathematical analysis. But the Penrose process requires carefully orchestrated particle trajectories, making it unlikely to happen naturally at high efficiency. In 1977, Roger Blandford and Roman Znajek discovered a more powerful mechanism. If a black hole is immersed in a magnetic field, the rotating ergosphere can act like a dynamo, generating electric currents that flow along the magnetic field lines. These currents tap the black hole's rotational energy directly, converting it into electromagnetic energy that powers a jet. This is the Blandford-Znajek mechanism, and it is brutally efficient. A maximally spinning black hole can convert up to 29% of its rest mass energy into jet power through this process. Phoenix A's jet is powered by this mechanism. Magnetic fields from the accretion disk thread through the ergosphere. The black hole's rotation twists these fields, winding them into tight helical structures. Electric currents flow along the field lines, accelerating charged particles to relativistic speeds. The particles are funneled. The jet is not matter being ejected from inside the event horizon. Nothing escapes from inside. The jet is powered by the rotational energy of space-time itself, just outside the event horizon, where the ergosphere extracts energy from the black hole's spin and channels it outward. The efficiency of this process depends on the black hole's spin. A slowly rotating black hole produces weak jets or no jets at all. A rapidly rotating black hole produces powerful jets. Phoenix A's jet, with its immense power output, tells us that Phoenix A is spinning near the maximum rate allowed by general relativity. The spin parameter, a dimensionless number between 0 for non-rotating and 1 for maximally rotating, is likely above 0.9 for Phoenix A. This means the black hole is rotating so fast that its equator is moving at nearly the speed of light. The ergosphere extends far from the event horizon, maximizing the volume of space where energy extraction occurs. But maintaining this high spin rate is difficult. Every bit the black hole's rotational energy. Over time, the black hole should spin down. The jet should weaken. Meal, every bit of infalling matter, adds angular momentum. If the matter falls in with the right orientation, aligned with the black hole's spin, it adds more angular momentum than the jet removes. The black hole maintains high spin, and the jet continues. This creates a delicate balance. Feed too little, and the jet drains spin faster than accretion replenishes it. The black hole spins down, the jet weakens, and the system shuts off. Feed too much, and the accretion disk becomes so bright it blows away the surrounding gas, starving the black hole. Phoenix A operates in the narrow window between these extremes, feeding at just the right rate to maintain high spin and sustain the jet indefinitely. This balance is not luck. It is a consequence of feedback. The jet itself regulates the feeding. When the jet is too powerful, it clears out gas, reducing accretion and allowing the spin to drop slightly. When the jet weakens, gas flows in more easily, increasing accretion and spinning the black hole back up. The system self-regulates, maintaining a quasi-steady state over millions of years. The magnetic field strength required to power Phoenix A's jet is staggering. Near the event horizon, magnetic fields must reach tens of thousands of Gauss, comparable to the strongest magnetic fields produced in laboratories on Earth, but sustained over volumes millions of kilometers across. These fields are generated by the accretion disk itself. As gas spirals inward, it drags magnetic field lines with it, compressing and amplifying the fields. Magneto-hydrodynamic turbulence in the disk, driven by the magneto-rotational instability, further amplifies the fields, creating a dynamo that sustains magnetic field strengths far beyond what simple compression alone could produce. The jet's collimation, its ability to remain narrow over hundreds of thousands of light years, is another puzzle. Jets should spread out, dissipate, lose coherence. Yet Phoenix A's jet remains tightly focused, a beam only a few thousand light years wide even at distances of hundreds of thousands of light years from the black hole. This collimation is maintained by magnetic fields. The jet carries a strong toroidal magnetic field, wrapped around the jet like a coil. This magnetic field creates a hoop stress, a pressure that squeezes the jet inward, preventing it from expanding. As long as the magnetic field remains strong, the jet stays collimated. But maintaining strong magnetic fields over such distances requires continuous energy input from the black hole. Phoenix A's jet is not a dying beam coasting on momentum. It is actively powered, continuously fed by energy from the ergosphere, even hundreds of thousands of light years away. The particles in the jet are accelerated to extreme energies. Cosmic rays detected in Phoenix A's radio lobes carry energies that rival the most powerful cosmic rays ever detected on Earth. These particles were accelerated somewhere in the jet, possibly at shock fronts where the jet slams into the intergalactic medium, or possibly in the jet's base near the black hole where magnetic reconnection events explosively release energy. The exact acceleration mechanism is still debated, but the result is clear. Phoenix A's jet is one of the universe's most powerful particle accelerators, producing particles with energies that dwarf anything human technology can achieve. And the jet has been running for at least 100 million years. Radio observations show the outer edges of the lobes, the oldest ejected material, are. At the jet's propagation speed, estimated at a few % of the speed of light, it takes over 100 million years for material to travel that far. Phoenix A has been firing continuously for longer than dinosaurs walked the Earth. The jet has outlasted entire evolutionary epochs, burning through rotational energy that, even for a black hole this massive, should have depleted long ago. Yet, it continues. Phoenix A is not winding down. It is in full operation, a cosmic engine running at maximum output with no shutdown in sight. The implications are chilling. Phoenix A is converting its own existence into destruction. Every second, the black hole loses a tiny fraction of its rotational energy to the jet. Over billions of years, this adds up. Phoenix A will eventually exhaust its spin, becoming a non-rotating Schwarzschild black hole, unable to produce jets, unable to tap the Blandford-Znajek mechanism. But that is trillions of years away. For now, Phoenix A remains a maximally spinning monster, feeding, spinning, and firing a jet that carves through space like a blade that never dulls. The galaxy that hosts Phoenix A is dying, not in the distant future, now. Star formation, the process that keeps galaxies alive, has ceased almost entirely. Where there should be glowing nebulae, stellar nurseries churning out new stars, there is silence. Cold. Darkness. The galaxy's spiral arms, if it ever had them, have long since been consumed or dispersed. What remains is a vast elliptical shell of ancient red stars, slowly dimming as they exhaust their nuclear fuel, with no new generation to replace them. Phoenix A has transformed its host from a vibrant stellar ecosystem into a cosmic graveyard. The culprit is feedback. When a supermassive black hole feeds, it does not just grow, it kills. The energy released by infalling matter, the radiation from the accretion disk, and especially the jet, all inject enormous amounts of energy into the surrounding gas. This energy heats the gas, sometimes to millions of degrees, making it too hot to collapse and form stars. In extreme cases, the energy is so intense it expels the gas entirely, blowing it out of the galaxy into intergalactic space. This is called AGN feedback, active galactic nucleus feedback, and it is one of the primary mechanisms that shuts down star formation in massive galaxies. Phoenix A's feedback is not subtle. The jet alone pumps 10 trillion solar luminosities into the intergalactic medium. When this jet plows through gas clouds, it does not gently push them aside. It shocks them, ionizes them, shreds them. Molecular clouds, the dense regions where stars form, are torn apart by the jet's passage. The molecules are dissociated into atoms. The atoms are ionized into plasma. What was once cold, dense, star-forming gas becomes hot, diffuse, sterile plasma that will never collapse under its own gravity. Star formation does not slow down. It stops. Observations of Phoenix A's host galaxy confirm this. Infrared surveys which detect the heat from dust warmed by young stars show almost no signal. There are no bright regions of recent star formation, no OB associations, no supergiant stars. Spectroscopic studies reveal that the galaxy's stellar population is old, with ages exceeding 10 billion years. The stars we see formed long ago in a brief burst of activity and then nothing. The galaxy has been quiescent, dead, for billions of years. Phoenix A has been sitting at the centre, feeding on the remnants, ensuring that no new stars ever ignite. The jet's impact extends far beyond the host galaxy. The radio lobes, those vast bubbles of plasma carved out by the jet, displace enormous volumes of intergalactic gas. This gas, normally available to fall into nearby galaxies and fuel star formation, is pushed away, heated, rendered useless. Simulations show that powerful jets like Phoenix A's can affect star formation in galaxies millions of light-years away, not by directly hitting them, but by heating and displacing the intergalactic medium they rely on for gas infall. Phoenix A is not just killing its own galaxy, it is sterilizing the neighborhood. There is a narrative anchor here, a way to make this personal. Imagine a planet in this galaxy, not near the center, not in the jet's path, but in the outer regions, orbiting a red dwarf star in the galaxy's halo. This planet, if it ever harbored life, would see a sky that grows darker with each passing million years. The bright spiral arms, the star-forming regions that once lit up the night, have vanished. The galaxy's core, where Phoenix A lurks, glows faintly in X-rays and radio, invisible to the naked eye but detectable by any civilization advanced enough to build telescopes. They would observe the jet, a thin line of destruction cutting across their sky, and realize that their galaxy is being consumed from the inside out. They would calculate, as we have, that Phoenix A has eaten the equivalent of 100 billion suns. They would measure the jet's power output and understand that their galaxy's ability to form new stars has been destroyed. They would look at the stellar population, ancient and dying, and realize that within a few billion years, the last stars will burn out. Their galaxy will become a graveyard of white dwarfs, neutron stars and black holes, orbiting a central monster that shows no signs of stopping. And they would face the existential terror of knowing that there is no escape, no way to stop Phoenix A, no way to reverse the damage. their galaxy's fate is sealed. Phoenix A's host galaxy is part of a larger structure, likely a galaxy cluster or group. These clusters contain hundreds or thousands of galaxies bound together by gravity. In a typical cluster, galaxies interact, collide, merge, and exchange gas. This activity fuels star formation and black hole growth across the cluster. But Phoenix A's presence changes the dynamics. The jet heats the intracluster medium, the hot gas that fills the space between galaxies. This heated gas becomes buoyant, rising away from the cluster center in vast plumes. X-ray observations of galaxy clusters with powerful central black holes show these plumes, cavities in the X-ray emitting gas carved out by jets. Phoenix A's jet has likely created similar cavities, displacing trillions of solar masses of gas and preventing it from cooling and falling into galaxies. This feedback loop is self-limiting in some clusters. The jet heats the gas, preventing it from cooling and feeding the black hole. The black hole starves, the jet weakens, the gas cools, and the cycle restarts. But Phoenix A seems to have found an equilibrium where the feedback is strong enough to prevent runaway star formation, but not so strong that it completely starves the black hole. The result is a dead galaxy with a feeding black hole, a paradox that should not persist but does. The galaxy's morphology provides more clues. Supergiant elliptical galaxies like Phoenix A's host typically form through mergers, multiple smaller galaxies colliding and coalescing over billions of years. Each merger delivers gas to the center, feeding the black hole, but also triggers bursts of star formation. Phoenix A likely grew during these mergers, consuming the gas before it could form too many stars. The galaxy's current state, massive but dead, suggests that Phoenix A won the competition. It ate faster than stars could form, draining the galaxy's fuel reserves and leaving nothing behind. There is also evidence of past violence. Tidal streams, faint arcs of stars pulled from smaller galaxies during past mergers, surround Phoenix A's host. These streams are the ghosts of galaxies that no longer exist, torn apart by gravitational forces and absorbed into the growing giant. Each of these mergers likely fed Phoenix A, delivering fresh gas and possibly smaller black holes that merged with the central monster. The galaxy we see today is the end result of billions of years of cannibalism, a graveyard built from the corpses of dozens of smaller galaxies. The lack of star formation has another consequence. Without supernovae, without stellar winds from massive stars, the galaxy produces almost no heavy elements. Elements like carbon, oxygen, iron, the building blocks of planets and life, are forged in stars and dispersed by supernovae. A galaxy without star formation is a galaxy where the chemical enrichment has stopped. Any planets that exist are relics, formed billions of years ago from gas that is now depleted. New planets cannot form. The galaxy is not just dying, it is fossilized, frozen in a state that will persist for trillions of years until the last stars fade and everything goes dark. Phoenix A sits at the center of this tomb, still feeding, still growing, indifferent to the destruction it has caused. The black hole does not care that it has killed its host. It does not care that the galaxy will never recover, it simply feeds, and as long as there is matter within reach, it will continue to feed, adding mass, maintaining spin, firing the jet that ensures nothing will ever live in this galaxy again. This is not a distant abstract tragedy. This is happening right now, 10 billion light-years away. The light we see from Phoenix A left that galaxy when the universe was much younger, when our own solar system had not yet formed. But the black hole is still there, still feeding, still destroying, and there is nothing that can stop it.